In this video, we'll start taking a look at the SaaS patterns. But before that, let's just discuss about a special case of PaaS, which is called as serverless. As the name suggests, serverless is alluding to the fact that you truly do not need to provision a server in order to use it. But it does not mean that you don't need a server to execute something. Obviously, anything that requires execution requires servers to be available behind the scenes to host the CPUs, the memories, etc. But this is from a perspective of the user. The user does not need to provision any server, and all that he or she needs to do is just provide the logic, and the logic automatically gets executed against any number of servers which are necessary in order for that execution to be successful. So serverless is a special case because it's just a very simplified version of a general purpose PaaS, but that simplification is extremely beneficial for certain kinds of workloads. So what are the workloads that can make use of serverless the best? So the workloads which are ideally suited for serverless are a combination of something which is very low in terms of complexity and in terms of latency, right? Has logic which is embarrassingly parallel, and finally can be triggered based on events which are which can be occurring and which can be monitored using standard services. So what does low complexity / low latency mean? Typically, this refers to the fact that each unit of execution of that logic that you've given it can be done in the order of seconds and doesn't take hours or days together. That's what this refers to. So low latency is the more important requirement of these two, and therefore low complexity is like a natural corollary. The embarrassingly parallel logic comes from the fact that in a serverless setting, that logic that you've provided needs to be executable on any machine that's available without having to worry about whether the data that's required for it is available locally or not. So, in a sense, if you need to do things like divide and conquer, then a serverless paradigm is not suitable for you. Because in a divide and conquer approach, the act of conquering requires the outcomes that are produced by each of the embarrassingly parallel divide steps to be aggregated again, which is not the case with serverless, right? Serverless is not suitable for it. Then the third element here is because each unit of execution is for the few seconds, as an example, and it's embarrassingly parallel, you want to be able to run this at any point in time based on trigger as opposed to based on schedule. Obviously, you could do it schedule based, but then there wouldn't be much of a point because it's just running for small seconds at a time. Better would be the more suited workload for serverless is trigger-based execution. So the example of trigger-based execution here would be, again, if you take the Indian Railways example, I'm making a booking on the website, but the moment that booking request is made, right, I need to be able to trigger a payment link so that I can act on the payment information. So that act of triggering for the payment part of the journey to be triggered, right? That's well suited for the act of triggering the payment is well suited for serverless, but the payment itself could be more complex, right? It depends on what is involved in that kind of a setup. Okay, so in a sense, serverless requires all three things. Rather, the workload needs to meet all these three criteria in order to be suited for a serverless-based mechanism to execute. Okay, the last of the patterns associated with cloud service provider options is SaaS, or software as a service. So these are, in effect, business-specific applications which are highly opinionated pieces of software which are integrating the platform and the hardware that's necessary for it to execute. so that the user who uses the SaaS software does not need to worry about any kind of provisioning, any kind of scaling, or any kind of fault tolerance or anything related to the non-functional aspects at all, right? So these are in effect users who are business folks, right? Who are people who are not developers. So these are more business driven. They are extremely sensitive to speed. They don't have any manpower for managing IT infrastructure or for answering questions related to why didn't this software work, why didn't this process work, etc. Right? They would prefer instead all of that to be outsourced and managed by somebody else, and the software, which is the SaaS software here, does it for them. Right? So in this kind of a setup, functional, non-functional, and cloud, all of it is integrated into one form factor, and it gets built using a meter which is directly, specific to the business. So, like I mentioned, Salesforce is one of the first examples of a SaaS software. They pioneered the world of CRM, but since then, of course, they have themselves branched into PaaS software, etc. Likewise, almost any single thing that you see as software today, which you consume on your daily basis, especially through apps, they're all SaaS software behind the scenes, right? Like Swiggy, Ola, Myntra, etc. All of them are SaaS software at the end of the day. Byju's, in the world of EdTech. So what are the SaaS software patterns really good for? They're extremely, advantageous for businesses where velocity is super critical, right? They want to roll out new features, and the SaaS software company is able to roll out features for all of their customers in one shot. No need to do separate testing cycles, no need to do separate scaling, performance benchmarks, nothing, right? Automatically gets rolled out in one go. Everybody consumes it together as part of one common multi-tenant deployment, right? Very high levels of predictability because you know exactly what to expect because everybody else is using the same software, right? You're not just using it custom tuned to yourself alone. Everybody else is using the same software. So the support that it gets, the predictability that it has, the stability that it has, all of that becomes rock solid as a result, right? Law of large numbers, essentially. Performance becomes something that you can almost take for granted. Again, because a lot of users, a lot of customers are there on top of it, a lot of businesses end up using it. There's a lot of attention that the SaaS company provides it. And the SaaS company is only dedicated to that, right? They're not doing like 10 other things. They're very specialized in their form factor. And finally, whatever the business needs done, they get a configuration interface. They don't need to write code. They don't need to develop software. They don't need to test it. They don't need to worry about platform configurations and things like that. It's just very simple business configuration, software configuration, extremely easy to manage. Now, the flip sides are that obviously you get the least control, right? You don't have absolutely any control at all on the hardware, no control on the scaling characteristics, on fault tolerance, nothing, right? So it becomes hard to understand what is happening behind the scenes. Vertical integration could be a negative because if you operate in the same vertical, you could want to have flexibility on how certain things are done or how regulation needs to be handled. So let's imagine, for instance, a SaaS company which is giving you a financial services software for accounting, right? And you're yourself a bank, right? If you're a bank, you're in the same space, you're highly regulated. You might not want to use the accounting software from a SaaS company because you might need to do your own regulatory requirements. You might need to do your own accounting, which is slightly more flexible, which requires some configurations changes to be done in the backend, which the SaaS company will not do for you, right? Because you operate in a market which is highly regulated compared to their typical clients which operate in a different market. So that could be an issue. And then the advantage about very high velocity of new features could be a disadvantage as well in some cases because it's not sometimes they're not tested very well. All right. So we spoke about the cloud at length in these series of lectures in this week. We spoke about how cloud native is a design principle that you should absolutely adopt because that's what gives you the ability to scale and meet your business requirements as a developer. And cloud native means writing software which enables loosely coupled systems which are observable, as a result manageable, as a result resilient, right? So having these three properties are very critical for a cloud native system. Now, we also spoke about the various kinds of services that are provided by cloud, be it infrastructure as a service, platform as a service, or software as a service, or SaaS. Now, let's tie it back together to the discussion on big data. What does big data in the era of cloud look like? Actually, it doesn't look all that different, right? We spoke about how big data evolved this concept of separating out storage from compute, right? MapReduce did that when Google published Google MapReduce and Google File System. Hadoop took it up and open sourced it and said, I'll call MapReduce as the Hadoop MapReduce implementation. That's separate from the Hadoop file system, or HDFS. So that way, the decoupling had already happened for big data to work correctly, for divide and conquer to work correctly as a strategy. So when cloud came about, cloud also emphasized the same thing. It was a natural marriage of sorts, right? Compute completely decoupled from storage, and this allowed the big data to also serve as a workload, which is completely independently planned and separately executed. And the storage associated with big data can be directly attached to can be directly mapped to the storage that cloud provides as a completely separate service, as a loosely coupled service. So as long as big data compute workloads know where the data is spread or how the data can be accessed, they can run wherever they run, right? Not a problem. So compute is scaled separately across a set of available resources. The cloud takes care of it, and parallelism therefore becomes a matter of how do you get access to the maximum amount of resources at the same point in time. And storage is scaled separately, completely independently. So this creates the loosely coupled environment that's suited for big data to execute within the cloud. So if you look at storage, the options in the cloud are many. In Google, it's called as Google Cloud Storage, or GCS. In Amazon, it's called as S3. But there are many other options as well. So in one of the later lectures, we look at all the different storage options, all the different data options. Where can you store data? Where can you retrieve data from, etc. But the default storage options available in the cloud is what's called as the object store. Object stores are effectively storage areas where you can store objects and retrieve objects. This is as opposed to the ANSI file system that we're all used to when we interact with our laptops, with Linux file systems, or with Windows file systems, right? In a nutshell, big data and cloud, very natural marriage, very closely linked to each other. And we saw examples when we spoke about the platform as a service options of how Spark itself is available as a regular PaaS service from some of these cloud options. In the rest of the course, we'll actually be using Spark PaaS for the most part. So, let's get ourselves exposed to it starting from the next lecture onwards. Thank you.